Okay, so we're going to continue with the heart and talk about the pathway of blood through the heart. So the heart acts like a pump, but it's actually two pumps that work simultaneously. On the right side, the right ventricle pumps blood to the lungs. And so it's called the pulmonary circuit. And the pulmonary arteries carry blood away from the heart to the lungs. The pulmonary veins carry blood back to the heart. On the left side, it's called the systemic circuit because the blood leaves the heart and goes to everywhere in the body, to all the systems, and then it comes back via the systemic veins. So all the tissues. There we go. So if we look at this, and I will draw and scan a diagram that's more simplistic than this that you can use when writing tests, and something that I used when I was a student, but it basically works like this. We can start anywhere because it's a circuit. You can start anywhere on it. So if we start here at the body, the capillaries of the body have dropped off the oxygen, picked up carbon dioxide, dropped off nutrients, and picked up waste products. This deoxygenated blood, the blue blood, flows back through the vena cava into the right atrium. It passes through the tricuspid valve into the right ventricle. From the right ventricle, it's pushed out through the pulmonary semilunar valve, through the pulmonary trunk and the pulmonary arteries, into the capillaries of the lungs, where carbon dioxide is dropped off, oxygen is picked up. This reoxygenated blood leaves the lungs through the pulmonary veins, ends up back in the left atrium, where it passes through the mitral valve into the left ventricle, and then on contraction it's pushed up through the aortic semilunar valve, out the aorta, and through all the branching arteries to get to the capillary beds of all the tissues where oxygen is dropped off and carbon dioxide is picked up. So it does this circuit over and over and over again. You'll notice that everything on the right side of the heart here has deoxygenated blood, and everything on the left side of the heart here has oxygenated blood. You'll also notice that everything above the valves, blood is entering the heart. Everything below this AV valves, blood is leaving the heart. So, right atrium, through the tricuspid, right ventricle, out pulmonary semilunar, pulmonary trunk, pulmonary arteries, lungs. Pulmonary veins, left atrium through the bicuspid, which is the mitral valve, into the left ventricle, out through the aortic semilunar valve, to the aorta, to systemic circulation. Now, what's interesting when we look at the pictures, it looks like the right side is actually smaller than the left. It's not. The volume is the same. Equal volumes of blood have to be pumped at each heartbeat, really, because you can't have one getting ahead of the other, because the output of one is the input of the other side. And so if, say, the right ventricle stop pumping as much, then not as much blood would return to the left, and so therefore there would be less to pump on the left. It balances out. If there is something wrong with the right or the left ventricle, then it doesn't pump as much blood out into the aorta, which means not as much blood returns to the vena cava, which means there's less blood for the right side to pump, and it balances out. Now, on the pulmonary side, it's not much of a job to pump blood from your heart to your lungs. It's, what is that? Maybe 4 inches, maybe 6 inches. It's not very far at all. So it doesn't need a lot of pressure. There's not a lot of resistance to overcome. On the systemic side, blood has to leave the heart and go right to your big toe and all the way back. Lots of resistance. It's a long circuit, and therefore it needs more force. So when we look at the anatomy of the ventricles, we're going to see that the right ventricle walls are much thinner because they don't have to produce as much force. The left ventricle is much thicker because it has to overcome the resistance of the systemic circuit. If you look at the picture, you can always tell the left ventricle in a cross-section because it's almost round, and the myocardium is really, really very thick. The right ventricle kind of has got this more or less triangular shape, and the walls, the myocardium, is much thinner. The lumen of this space and the lumen of that space are the same because they do pump the same amount of blood. So the heart itself doesn't get any oxygen or nutrients from the blood that's being pumped through the chambers. It needs a blood supply to bring oxygen to the cardiac muscle cells so that they can use it to make ATP so that they can contract. And so there's circulation that actually feeds the walls of the heart itself, the myocardium itself. And this is called the coronary circuit. There are a lot of different variations in the arterial supply. There are anastomosis, which means blood vessels joining without capillaries. There is back kind of almost detours built into it, collateral routes, etc. But there's fundamentally, most people have the same fundamentals at least. So on the arterial side, coming off the aorta, right at where the aorta starts, there are 2 blood vessels, 2 arteries, the right and the left coronary artery. And this happens in the AV groove or the coronary sulcus, whichever you want to call it. So on the left side, the left coronary artery immediately branches into one that circles around the back in the coronary sulcus. It goes left, and so it's between the left atrium and the left ventricle, and it circles around to the back of the heart. And that's called the circumflex, which means circles and bends. And the other branch ducks down the front in the interventricular septum and sends branches to the front part of the ventricles on both sides. And that's where it becomes variable in most people. On the right side, the right artery becomes the marginal artery and the posterior interventricular, and feeds the back of the ventricles, and it passes down the posterior interventricular sulcus. The veins are much more variable, and we're not going to worry too much about them, but there's the great cardiac vein, the anterior cardiac vein, the small cardiac vein. We'll see pictures of that in a second. Again, this is more variable. But all the veins, we'll start out here. So left coronary artery becoming the circumflex going around the back, and the anterior interventricular. The right passes around here, will become the posterior interventricular here, and the marginal here down the right margin of the. These all have names as well, but they're variable, so we're not going to worry about it. You'll also notice that the anterior interventricular joins onto the posterior interventricular. So if there was a blockage here, blood could go all the way to there, even though it normally comes to here. The circumflex actually meets the right coronary artery here at where the posterior interventricular starts. And there is usually an anastomosis there. But this feeds the blood supply to virtually the entire heart. The veins pick up here. So this is the middle cardiac vein. The great cardiac vein is this one that feeds into this thing called the coronary sinus. Right? The anterior cardiac veins and the small cardiac vein runs along with the marginal artery. It feeds back into the sinus. A sinus is almost the same as a vein. It has the same endothelium. It's got the same or very similar body wall. What it's lacking is valves. Anytime we see something called a sinus, it acts like a vein. It collects blood and directs blood back towards the heart. However, there are no valves. To be a vein, you need to have valves. So this coronary sinus is like an enlargement of the vein with no valves, and it collects the blood up, and then the blood enters the right atrium right here at the where the coronary sinus comes in. Okay, from the back, and this is the first time we've seen a picture of the back. So to orient, there's the aorta. The pulmonary trunk is up here. The left and right pulmonary veins is here. Superior vena cava, inferior vena cava. The four pulmonary veins going back here. This is the back of the left atrium. The right atrium is here. There's the auricles of the two. This is the sulcus here. This is the right coronary artery, becoming the posterior interventricular artery down here. The middle cardiac vein coming up here to the sinus. The great cardiac vein coming to the sinus. Posterior cardiac vein, or coronary vein, which sometimes it's called, ends up here in the sinus, and then the sinus dumps here into the right atrium, right beside the inferior vena cava. Okay, valves. Valves make the blood flow in one direction. This is very important. If any of you have ever worked as a server in the restaurant, you know that restaurants have usually two doors going into the area where the servers go to the kitchen. And they open in opposite directions. It's to ensure one-way flow so that waitstaff don't bump into each other. There's kind of an entrance door to the area, and there's an exit door to the area. And they push open, so people going in push the door into the space, people leaving push the door out of the space. It prevents backflow. So there are two atrioventricular valves, which we've already talked about. So when the ventricles contract and blood pressure in the ventricle goes up, these valves close. And they don't allow blood to go back into the atrium. So on the right side, the tricuspid closes and makes blood not go in back to the right atrium, but instead pushes it out into the pulmonary trunk. On the left side, the mitral valve closes, prevents blood from going back to the left atrium, but makes it instead go out to the aorta. Now you can imagine that these valves have to resist a lot of pressure. There's enough pressure to push blood all the way to your toes on the left side. It's a huge amount of pressure. The problem then with the mitral valve is that there is this possibility that the pressure could blow that valve backwards right through and then be not preventing blood from flowing back into the atrium. And the atrium would be the path of least resistance, and therefore blood wouldn't flow to the body. So it's very important that these valves stay patent, stay functional. The same on the right side, but there's not as much pressure, so it's not as big a danger. So one of the ways that the body solves this is by basically tying strings of connective tissue to the cusps of the valves, and then attaching the other ends of the strings to the papillary muscles. So when the heart contracts, the muscles, the papillary muscles contract, and papilla actually means nipple, so that's why they're called papillary muscles. It pulls on these little tendon type things, these tendinous cords called the chordae tendini, which prevents the cusps of the valve from blowing backwards. It acts as kind of a doorstop and prevents the prolapse of these valves. They're very important. Yeah, I'll talk about them more in a second. On the outflow, there is valves that point the other direction. These are called the semilunar valves. They prevent backflow into the ventricles when the ventricles are relaxing and filling with blood. You want the mitral valve to open so that the blood will flow from the atrium to the left ventricle, but you don't want any blood that you've just pumped into the aorta from flowing back into that ventricle and refilling. You want it to be one way. So you put up the door, you put up these valves. And that's what the aortic semilunar valve does. It prevents the backflow from the aorta. And the aorta has a fair amount of pressure in it at the time. This is what they look like if you were to take off the atrium and look down on the heart. It's a photograph of the same thing. So these are the cusps here. So you can see that the mitral valve has two cusps, 1, 2, and the tricuspid has 3, 1, 2, 3. The angle's not really good. The semilunar is here, and you can see that it goes the opposite direction from these. So this is the papillary muscle and the chordae tendini. And they prevent that valve from blowing backwards. So when the heart contracts, these tighten, which tighten these strings, which prevent the cusp from failing backwards. These are your heartstrings. When people are tugging on your heartstrings, that's what it means. These are collagen fibers. One of the problems with that we will see in pathology especially is when people have strep throat, when there's a streptococcal infection, one of the antigen proteins on a streptococcus bacteria is very similar to collagen. So sometimes the immune system, as it's attacking the strep, will actually attack collagen. And that's why strep throat is dangerous. The main thing that we're worried about, so what will happen is that your immune system will attack the collagen of the dermis of your skin, and the skin will get all inflamed, and that's why they call it scarlet fever. It's not that streptococcus is in the skin, it's the immune attack starts attacking the skin. At the same time, sometimes it's called rheumatic fever because it will attack collagen fibers everywhere. One of the problems is if it attacks the chordae tendineae and weakens, it can actually permanently damage the heart valve, and you can end up, a lot of people end up with mitral valve problems because of a streptococcal infection that has caused rheumatic fever. And the target of that are these chordae tendineae. You can see that it's all collagen. It's white. You'll also notice in this section how thick the myocardium is of the left ventricle compared to the right ventricle, because this requires so much more pressure to pump blood everywhere in the body. So when the heart is relaxed, this valve opens, blood flows into the chamber. When the pressure goes up as the ventricle starts to contract, it squeezes the blood. That pushes against the valve cusp here, which fills like a parachute, pushing up against and sealing off this opening. And the chordae tendineae here prevent this from actually failing and pushing backwards through. On the semilunar side, when there's lots of pressure in the ventricle, it pushes these valves open and blood flows into the aorta or the pulmonary trunk. When the pressure drops in the ventricle, as the ventricle is relaxing, the pressure in the trunk or in the aorta is greater, which then means that the cusps fill up like parachutes again and seal and prevent the blood from going backwards into the ventricle.